Hello everyone. In this video I want to show you something nice. So I made the pendulum using second generation blocks in Simscape here. So if you watched my previous video you saw that I made the pendulum using the multi-body blocks. But these are the second generation blocks where you don't need to make a physical object and they don't have animation, but they are very fast and good for simulation of physical systems. So you have an inertia block, you have a damper block, you have a spring block, ideal sensors, ideal actuators, and so on. And it is quite a bit easier to simulate the system with these. And to make it more interesting for you, I tried to add a few other things to make it more realistic. So if I want to control the angle of a pendulum from its initial angle, which here I set it at about 20 degrees, and I want to give it a torque so it goes to 30 degrees. So I want the angle to increase, because if you let it go under its own weight, it's going to go down. But here I want to apply such a torque that it goes to 30 degrees and staying there at 30 degrees. So I can do it through a PID control here. So I compare the actual signal that I measure from the pendulum using an encoder and compare it against the desired to get the error, send that error to a PID control, which gives me a voltage, then apply that voltage to a brush DC motor to give me the torque, and then apply that torque on the pendulum. So here I have added a bunch of extra things for you here. One is the control, one is the actuator, the model of a DC motor, and then an encoder which has some noise. So to simulate the noise, I added this band limited wide noise with a noise power of 1e to the negative 4. So I don't assume that my encoder is perfect. And then the controller, as I said, is a simple PID block, and my actuator here is this block. Again, this is a second generation block called DC motor. And I control the voltage to the armature of the DC motor through the input from the controller, right, through the voltage of the PID. And since that voltage is a Simulink block, I convert it into physical system. And then to apply a variable voltage to the armature of the DC motor, I use this block, which is called control voltage source. And you can find it under electrical under Simscape. And here I control the voltage of this armature through the PID. And this block, if you double click on it, there are lots of things that you can specify. For instance, you can model the thermal of the system too, thermodynamic properties. Here we assume that we are not going to model the thermodynamic effects. So what we need to provide is the resistance and the inductance of the armature, the torque constant, or you can also specify the back EMF. And then you can also provide the rotor inertia, the rotor damping. If you have initial rotor speed, you can provide all of them. And to make it more realistic, I provided the data that I have in one of my robotics lectures, if you watched, where I showed the effect of the gearbox and motors and everything on the equations of motion for a robot. At the end of it, you see these spec sheets for the Pitman DC motors. And here I use this data. So I neglected the Coulombic friction, but I added the viscous damping. I added this rotor inertia, so I used these two numbers. And then the other numbers I used is this number, torque constant. Then the other things I used is this terminal resistance, and then this terminal inductance, which is in millihenry. And the other thing I also used is this guy here, a gearbox ratio, which is 5.9 to 1. Again, I neglected efficiency. I assume that is 100%, but if you want, you can also model that as well, okay? So here I'm using the data from a real DC motor, and I plug them all in here. The only thing you see I have changed here is the torque constant. I multiplied it by 5.9, and that is the gear ratio. Because this DC motor block does not allow you to, does not have a field for a gearbox ratio. So it can bump up the torque and reduce the RPM, So what I did, I multiplied that by the torque. So I'm artificially in this block adding that gearbox ratio. I'm adding the torque. And if you want to include the efficiency, you can multiply that number here as well. Okay, so if you want, if it's 81%, you can say multiply by 0.81. And this brings your effective torque a little bit down. But again, if you want to plug in efficiency, you can do that. Okay, so this is going to send the torque out, and then I got that torque and applied it directly to my inertia here. This is a pendulum with a mass of 1 kilogram and a length of 0.2. So you see the inertia of it is mls squared, 0.1 times 0.2 squared. And the other thing you have here is this inertia. You can provide initial torque or initial velocity for it, not initial angle. The second thing is you cannot, in this inertia block, apply the component of the weight, the torque of the weight of the pendulum, which is negative mgl sine theta. Okay, I mean, there is this block called a pendulum, and if you want, you can find the pendulum. Okay, I guess it was called a linear pendulum or something. And you can do that, but you don't have all of these extra options. So I consider it to just be a slender bar here. And that extra torque due to gravity, when I got my theta, when I sensed the theta of this rotational element, I brought it, get a sine out of it, and then multiplied it by negative mgl. So this is that torque, and I added that extra torque onto what? The inertia. So this is the torque due to what? This is the torque due to DC motor, right? And then this is, so I can say motor torque. And then this one is the torque due to gravity, and I apply both of them to the inertia. The torque from the DC motor is already a second generation block, so I can directly wire it in. But the torque due to this mg sine theta, I have to convert it into a second generation block using this block here called ideal torque sensor. So this is a torque that is controlled by an external signal, and I convert that signal into second order through this block, which is called a Simulink to PS converter. So here, this is the torque of that. This is this torque. Both of them are applied. I also added a damper for the shaft of the pendulum, and I put 0.01 for the viscous damping of that. Then I use this block, which is called ideal rotational motion sensor, and you can measure the position, velocity, or acceleration of the shaft. And the angle you see here, I use this 108. Why? Because I have a gear ratio, remember, of 5.9, so my angle should be reduced by a factor of 5.9. So if I use 108 here, the output angle, the real output angle of the pendulum is going to be 20 degrees. And this is what I want to start with, 20 degrees. And the signal that it measures is in physical system, so I use this other block which converts the physical system into Simulink, as you just saw it. Okay, this guy here. And now it is going to be sent out, and I'm going to compare it with my, by adding some noise from the encoder, by compare it against the desired theta of 30 degrees, which is a constant. Okay, so this is all my system, and my PID control block is, of course, a block for which you can specify your parameters, your KP gain, your KI gain, your KD gain, and it also has a low pass filter to filter out the noise. If you use n of 0, you should not really do it. If you use n of 1, then it's just S over 1 plus S. If you use a bigger N, then the cutoff frequency of the low pass filter is going to change. So you can change the cutoff frequency of the low pass filter using this filter coefficient. And we definitely want to use that because our measurement from the encoder does have noise, and you always have noise in a physical system. Okay, so everything is, you see, I implemented everything for you so you can see it, and then we simulate the system for 60 seconds. Now I added some efficiency. Let's see if it's still, yeah, it is still going good. So the blue one is the desired 30 degrees, and the yellow one is the actual theta, which should start around, yeah, I made a mistake here. This should be 118, not 108, because it's divided by 5.9, not 5.4. So now it should start at 20 degrees, and let's see here. And then it goes to 30 degrees. And if you want to have a settling time here, right? If the settling time is 2%, 2% of 30 degrees is 0.6. So plus minus 0.6 is going to be from 29.4 to 30.6. And clearly you see that you're entering this range at a little bit over 1 second. So you are inside the plus minus 2% error after what? After a little bit, I would say over 1 second, probably 1.1 or 1.2 seconds. You are within 2% of the final answer, and if you want to be within 1% of the final answer, which is 29.7 and 30.3, then your time is about 1.34 seconds, and clearly after about 1.45 seconds or so, you are even less than that. You are within plus minus 0.2 degrees of the final 30 degrees. And most of the time your sensor probably cannot even measure 0.2 degrees. So you see clearly that very fast you are going to what? Go to the final value. Although you have noise, clearly you can see the noise in the actual data, right? You clearly can see the noise, and it's not really bad noise, but it is a noise. And by tuning your PID controller, by changing the KP, KD, and KI, I already tuned it. And although this is not like the best response, but this is a reasonably good and fast response. And here I could get what? I could get my system to work. And here you really cannot have a transfer function to use the tune option, because your pendulum is nonlinear and your angle is way more than 6 degrees. Okay, so you have to assume the system is nonlinear. So this is an overall example where I used second generation blocks. And the second generation blocks, I talked so much about it. They are, as I said, they are under Simscape. If you go to Simscape, you see that Simscape has lots of areas. This is the multi-body I showed you, and this is the electrical. But also, in addition, where under electrical you have the electromechanicals, and under that you have what? You have the brush DC motors, and of course I use the DC motor here. There are other types of motors here. So this is the block I use for DC motor. And then under foundation library, if you go under mechanical, under foundation library, you can go and find the rotational elements here. You see, that's a rotational damper. This is the reference for angle. This is the inertia. If you want, you can add a rotational spring. Then if you go under sources and sensors, under sources, you see here that is ideal torque source that I used, and this is what? Ideal rotational motion sensor. Okay, so most of these blocks that I used, they are here, and these are called second generation blocks, and you do not really need to provide much of graphics. Of course, they do not show you animation at the end, but hopefully you saw that this is a close simulation to an actual physical system. Thank you so much for your attention. I'll see you in the next video.